Let me ask you something. Pick up a jar from your kitchen. Any old jar. Pour out whatever's in it. Pour it all out. Hold it up to the light. Now tell me what's inside. Most of you will say nothing. The jar is empty. There's air in it, sure. But if I asked you to make it really empty, you'd pump the air out. And then? Nothing. A perfect vacuum. Job done. I'm here to tell you that you've just held in your hand the most violent, churning, energetic stuff in the entire universe. And nobody mentioned it. The space inside that jar, the nothing you just confidently dismissed, is more active than the surface of the sun. Particles are appearing and disappearing trillions of times every second. Fields are flickering. Energy is sloshing around in numbers so large the math breaks the laws of physics themselves. And if that nothing decided one day to flip, if it slipped from one configuration to a slightly more comfortable one, the universe would end. Not as a metaphor. Actually end. A wave moving outward at the speed of light, erasing everything it touches. So we're going to look at this nothing, carefully, layer by layer. And I promise you, by the time we're done, you will never look at an empty room the same way again. You'll wonder how you ever thought it was empty in the first place. Let's start with the obvious. The jar isn't really empty when you pour out the milk. There's air in there. About 10 million trillion molecules of nitrogen and oxygen rattling around in something the size of a coffee mug. They're moving fast too, roughly 500 meters per second on average, which is faster than a passenger jet at cruise. So already, what looked like nothing was secretly a tiny city of bouncing things, and we just didn't notice, because we couldn't see them. Fine. Get a vacuum pump. Hook it up to the jar. Suck out the air. Work hard at it. Pump and pump and pump. The best laboratory vacuums on Earth can get down to maybe a few hundred molecules per cubic centimeter. To compare, ordinary air has about 25 quintillion molecules in that same space. So we've removed almost everything. Almost. Now, you might think we're done. The pump is running, the gauge reads 0, the inside of the chamber is, by any reasonable definition, empty. But the walls of the chamber are still warm. They're glowing. Not in the visible part of the spectrum, but in the infrared. Your own skin is doing the same thing right now. You're radiating light constantly, and you can't even tell. So our chamber, even with the air gone, is full of an invisible soup of photons bouncing back and forth between its glowing walls. We cool it. Surround the chamber in liquid helium. Bring it down to a hair above absolute zero. The walls stop radiating. The infrared dies away. The inside is dark and cold and empty of matter. Surely now we have nothing. Surely. Here's where the trouble begins. We're going to step into the wall of that chamber for a moment. The wall is made of atoms. The atoms are arranged in a lattice, the way bricks are stacked in a building, only neater. Each atom is jiggling around its little position. They jiggle because they're warm, and warmth, if you really get down to it, is just jiggling. So at higher temperatures, the atoms jiggle more. At lower temperatures, they jiggle less. You might guess, sensibly, that if you cool everything to absolute zero, the jiggling stops. It doesn't. This is one of the most quietly astonishing facts in all of physics, and most people who haven't studied quantum mechanics have never heard of it. At absolute zero, the lowest possible temperature, the temperature where classical physics insists all motion must halt, the atoms are still moving. They have something we call zero-point energy. They cannot be still. The universe will not allow it. Why? Why won't the universe let an atom sit still? To answer that, I need to introduce you to a man named Heisenberg and a principle that has more attitude than a teenager. Werner Heisenberg, in 1927, figured out something that took a long time to sink in even among physicists. He was working in Copenhagen with Niels Bohr. They were trying to make sense of the strange behavior of atoms, which by the mid-1920s had begun to behave in ways nobody could explain with the old physics. Heisenberg's insight came as a kind of answer to a question that physicists hadn't quite known to ask. Not what does the world really look like at small scales, but what does it even mean to ask that question? He realized that there's a fundamental limit to how much you can know about a particle. Not a practical limit, not a we need better instruments limit, but a deep, baked into the cake limit. If you know exactly where something is, you cannot know how fast it's moving. And if you know exactly how fast it's moving, you have no idea where it is. Now think about that for a second. Imagine I told you that about your car. If you know what street you're on, you cannot know your speed. You'd think I was crazy. But that's how the world works at very small scales. It's the truth of nature, and the universe insists on it. There's a sister to this rule that's even stranger: time and energy. If you measure something for a very long time, you can know its energy with great precision. But if you only measure it for a tiny sliver of time, the energy could be anything. The energy is fuzzy. It's not just that you don't know it. It is fuzzy. Nature itself doesn't know. A musician understands this trade-off without realizing it. A long, sustained note has a clear pitch. Strike a clarinet for an instant, and the listener can't quite tell what note you played. The note has been smeared into a range of frequencies. Heisenberg's rule is the same idea, but baked into reality itself. Quantum mechanics is built on this kind of trade-off. Nature trades knowledge for knowledge. You cannot get something for free. So now ask, what about empty space? What's its energy? Well, you'd think, empty space, no stuff, energy is zero. Easy. But Heisenberg's principle won't let it be exactly zero. If the energy of a region of space is locked in at exactly zero for any length of time, then we'd know its energy precisely, and we'd know it forever. And that violates the rule. Nature has to leave wiggle room. The energy in any tiny piece of space has to fluctuate a little bit, bouncing above zero and below zero on tiny time scales we can barely imagine. This is not a theory. This is not a guess. This is the consequence of a principle so well tested that if it were wrong, modern electronics would not work. Lasers wouldn't work. The whole picture of how atoms emit and absorb light would collapse. Heisenberg is right, and the implication is enormous. Empty space cannot be empty. The math forbids it. Now, what does it mean for the energy of empty space to fluctuate? What does that look like? Energy and matter are connected. Einstein told us that. Energy and mass are two faces of the same coin, related by a famous little equation. So if energy is bouncing around in empty space, mass can bounce around too. Particles can flicker into existence and flicker right back out, as long as they don't stick around long enough to be caught. Picture an empty parking lot at midnight. Now imagine, for the briefest possible flash, a car appears in one of the spaces. It exists for a billionth of a second. Then it's gone. No tire tracks. No witnesses. Did it really exist? In a sense, yes. In a sense, no. We call these virtual particles. They're not full citizens of reality. They're more like the universe's bookkeeping errors, the rounding noise of existence, the little scribbles in the margins of the equations. But here's the thing. There are an awful lot of them. The vacuum, the so-called nothing, is teeming with these flickering ghosts. Every cubic centimeter of empty space has, at any given instant, virtual electron-positron pairs, virtual photons, virtual quarks, virtual everything. The vacuum is not a void. The vacuum is a foam. If you could shrink yourself down small enough to see this foam, you would not see darkness. You would see a wild, churning, frothing chaos. Like the surface of a boiling pot of soup. Like a thunderstorm at the molecular scale. Like a kitchen during the dinner rush, only nobody's eating, and the pots vanish faster than you can name them. You may have seen the little drawings physicists make of these processes. Lines come in from one side, representing real particles. They meet at a point, and from that point a wiggly line goes off and joins another line somewhere else. The wiggly line is a virtual photon. Sometimes the diagrams have loops, where a virtual particle appears out of nothing, goes around in a tight little circle, and dives back into nothing. Loops are the universe's way of doing scratch math behind the scenes. They affect the answer. To predict what really happens in a given measurement, we add up all the diagrams, the simple ones and the complicated ones, and we get our final number. The vacuum, with all its loops and all its wiggles, contributes to every prediction we make. But hold on, you might say. This sounds like a fairy tale. Particles popping in and out, sure, prove it. Show me a measurement. In 1948, a Dutch physicist named Hendrik Casimir was thinking about exactly this problem. He had a thought experiment. Take two flat metal plates, put them very close together, but not touching. According to classical physics, nothing should happen. Two parallel plates, no charge on them, no fields, just sitting there in a vacuum. Boring. But Casimir realized something marvelous. Between the two plates, the virtual photons of the vacuum can only fit if their wavelengths divide neatly into the gap. Most wavelengths don't fit. They're excluded. Outside the plates, all wavelengths can wander freely. There are more virtual photons outside than inside. The outside is pushing harder than the inside. Result: the plates are pushed together. By nothing. By the absence of certain virtual photons. Imagine two ships floating very close together on a choppy sea. The waves outside the gap between them slam into their hulls from outside. The waves inside the gap, because of the narrow space, can only fit if they're short enough. There are fewer waves between the ships than there are around them. The result: more wave pressure outside than in. The ships drift toward each other. Sailors knew this in the 1800s. They had to be careful with parallel ships in heavy weather, especially in calm spots between storms. The Casimir effect is the same physics, only with the choppy sea replaced by the quantum churn of the vacuum, and the ships replaced by metal plates. Nothing pushes things together, or rather less nothing on one side than on the other. Now this sounds like a tall tale. Two metal plates pushed together by ghosts. But people went and measured it. The early experiments are very tricky, because the gaps have to be unimaginably tiny and the plates have to be polished as flat as the technology will allow. The first attempts gave results consistent with Casimir's prediction. Better experiments confirm the prediction with increasing accuracy. The Casimir force is real. It's a measured, documented phenomenon. Engineers worry about it now, because as we make smaller and smaller machines on the scale of a single bacterium, the Casimir force starts to matter. Tiny components stick together because of the empty space between them. Let me pause and let that sit. Two pieces of metal, separated by vacuum, are pulled together by the structure of nothing. The thing in between them is pushing them. The thing in between them is, by classical reckoning, pure absence. If somebody had told me in 1940 that I would one day discuss a force generated by absence, I would have laughed. But the universe does not care what we find amusing. The Casimir effect is striking, but it's just one signature of the active vacuum. There are others, sharper ones, better measured. Take an electron. The electron is the most familiar particle in your life. Every electric current is a flow of them. Every chemical bond involves them. Every atom in your body has them whirring around the nucleus. We've studied electrons for almost a century. We know them well. An electron has a property called its magnetic moment. Think of it as how strong a tiny magnet the electron is. According to a beautiful equation by Paul Dirac, written down in 1928, the electron's magnetic moment should have a precise value, a clean, simple number. The theory predicted it. The number was elegant. When experiments got good enough to measure it, the experimenters found something off. The electron was a slightly stronger magnet than Dirac said it should be. Just by a smidge. About 1 part in 1,000. Was Dirac wrong? Sort of. He was right about the bare electron. The trouble is, you can never observe a bare electron. The electron you measure is always surrounded by the active vacuum. Virtual photons flicker around it. Virtual electron-positron pairs blink in and out near it. The electron is constantly being dressed in a fizzing coat of virtual nothing, and that coat changes how it behaves. Calculate the dressing, using quantum electrodynamics, the theory I had a hand in building, and you predict the magnetic moment with fanatical precision. Compare theory to experiment. They agree to remarkable accuracy. Let me give you a sense of what that means. Imagine the distance from New York to Los Angeles. About 4,500 kilometers. Now imagine measuring that distance from one end to the other. And your measurement is off by less than the width of a human hair. That is roughly the level of agreement we have between the theory of the active vacuum and the measurement of the electron's magnetism. Nothing else in science comes close. We are right about the active vacuum. And we have receipts. You feel that? You feel how solid the ground under us is? The vacuum is bustling with virtual activity. We can predict its consequences to absurd precision. The bookkeeping errors of empty space are not noise. They are signal. They are part of how the world works. Now we're going to go further. We're not done. Not even close. Up until now, I've been talking about quantum fluctuations as if they were the only weird thing about the vacuum. They aren't. There's another whole layer, and it's responsible for one of the most basic facts of your existence. You have mass. You weigh something. The chair you're sitting in weighs something. The earth weighs something. Where does that weight come from? You might think, well, we're made of atoms, and atoms have mass, so that's where weight comes from. True. But where do the atoms get their mass from? The protons and neutrons in the nucleus, mostly. About 99% of your mass is in those protons and neutrons. And those protons and neutrons are made of quarks, held together by the strong nuclear force. So most of your mass is, weirdly, the energy of the binding glue, not the particles being glued. But the quarks themselves have a small intrinsic mass. So do electrons. So do most of the fundamental particles. And here's the question. Where does that intrinsic mass come from? For a long time, nobody knew. The standard model of particle physics, beautiful as it is, doesn't naturally make particles with mass. The math wants them to be massless. They should fly around at the speed of light, the way photons do. But they don't. They're slow. They have weight. Why? In the 1960s, a handful of people, including one fellow named Peter Higgs, suggested an answer. They said, maybe the vacuum itself has a property. Maybe everywhere in the universe, even in the deepest emptiness, there is a field. Not a force you can feel directly, but something more like a thick, invisible molasses that fills all space. Particles moving through this molasses get slowed down. The slowing down is what we experience as mass. The heavier the particle, the more it interacts with the molasses. The lighter the particle, the more it slips through. That field is now called the Higgs field. And the molasses, if the theory is correct, is on all the time, everywhere. Even in your jar. Even in deepest intergalactic space. The theory predicts that there should also be a particle that goes with the field, a Higgs boson, and finding that particle would be the strongest possible confirmation. The accelerators we have right now are not quite powerful enough to make one. Bigger machines are being designed. Sometime, perhaps in the next decade or two, perhaps later, we'll know whether this picture is right. But suppose it is. Then think about your jar again. Pour out the milk. Pump out the air. Cool it to almost absolute zero. Block out all the photons. You think you have nothing. But everywhere in that jar, the Higgs field is humming away, filling every cubic millimeter, giving every passing particle its mass. The vacuum is wearing a coat that you cannot remove. You couldn't get rid of it if you tried. Empty space is not empty. Empty space is dressed. Now we come to the part that gets really uncomfortable. Because if the vacuum is full of energy, real, measurable energy, then that energy ought to do something. Energy bends space, according to Einstein. Energy gravitates. So the vacuum, being full of energy, should bend space. The whole universe should be experiencing a force from the energy of nothing. Einstein wrestled with this question back in 1917. He had just finished his theory of general relativity. He looked at his equations, and he noticed something. If the universe contains matter, and matter has gravity, then the universe should be either expanding or collapsing. It can't sit still. Einstein, like most people of his time, believed the universe was static. So he added a term to his equations, which he called the cosmological constant. It was a kind of anti-gravity built into space itself, just enough to balance gravity and keep the universe at peace. Then Hubble showed the universe was expanding. Einstein's anti-gravity was no longer needed, and he called it the biggest blunder of his life. The cosmological constant was set to zero, and most physicists forgot about it. But then quantum mechanics came along, and quantum mechanics says the vacuum has energy. It cannot be empty. And energy, by general relativity, gravitates. The cosmological constant is back, and it's not a free parameter we can set to whatever we want. It should be calculable from the energy of the vacuum. So we calculate. We add up all the zero-point energy from all the fields. We get a number. The number is enormous. It's so enormous that, if it were correct, the universe would have torn itself apart less than a second after it began. Galaxies could not have formed. Stars could not have formed. You couldn't be sitting where you're sitting. But you are sitting where you're sitting. The universe is here. It's billions of years old. So either our calculation is wrong, or some unknown mechanism is canceling almost all of that vacuum energy and leaving only a tiny remainder. The size of the remainder, set by what we observe in the cosmos at large, is small. The size of what theory predicts is unimaginably large. The two numbers are off by a factor of about 10 to the 120th power. Now 10 to the 120th is not a number you encounter in daily life. It is 1 followed by 120 zeros. It is more than the number of atoms in the visible universe. It is more than the number of seconds since the Big Bang multiplied by the number of grains of sand on every beach on Earth. It is, in a real sense, beyond conception. Imagine you're a chef. You measure out, in your kitchen, exactly enough salt for a single bowl of soup. You tell your assistant the measurement. Your assistant goes to the storeroom, returns with a bag, and the bag contains more salt than has ever existed in the history of the world. That's roughly the level of disagreement between what theory predicts and what observation tells us about the vacuum's energy. Either the chef is wrong, or the assistant is wrong, or our entire idea of what salt is needs revising. Some physicists think there must be a deep, hidden cancellation, some structure of nature that conspires to make almost all that vacuum energy invisible. Others think we're calculating wrong. Others think the universe might be one of many possible universes, and we're in a rare patch where the vacuum energy happens to be small enough for galaxies to form. Nobody knows. It is an open mystery, and one of the most important unsolved problems we have. So when I tell you the vacuum is full of energy, please understand we know that it is. We don't know how much. We don't know why the calculation we make is so wildly different from what the universe seems to allow. We are walking around in a haunted house, and we have only just begun to count the ghosts. But this isn't even the most disturbing thing about the vacuum. The most disturbing thing comes when you ask whether the vacuum we live in is the only one possible. Think about a marble in a bowl. The marble rolls around. Eventually, friction takes over, and it settles at the bottom. The bottom is the lowest energy state, the stable place, the place the marble wants to be. Now imagine a different bowl. This bowl has two depressions. There's a shallow dip up high, and a deeper hole down below, separated by a small ridge. A marble in the shallow dip is at rest. It's not moving. To a casual observer it looks settled, but it isn't really at the lowest possible energy. The deeper hole below would be lower. The marble is in what we call a metastable state. It's stable, sort of, until something jostles it over the ridge. Then it rolls down to the deeper hole and stays there. Now apply this picture to the vacuum. The Higgs field, the molasses I told you about, has a particular value everywhere in the universe. That value sits at a minimum of the field's energy. We assume it's the lowest minimum. We've been assuming this for a while. But what if it isn't? What if the vacuum we live in is the shallow dip, and there's a deeper one we don't know about? Then the universe is a marble sitting in the wrong hole. It's been sitting there for billions of years, peacefully, while humans and stars and galaxies have arisen on top of it. But it could, in principle, slip, tunnel quantum mechanically over the ridge. or be jostled by some unimaginable disturbance. If it slipped, what would happen? A bubble of true vacuum would form. Inside the bubble, the Higgs field would have a different value. The masses of all the particles would be different. The forces of nature would be reweighted. Atoms would no longer hold together the way they do. Chemistry would not work. Biology would not work. The bubble's interior would be a place where matter as you know it cannot exist. The bubble's wall would expand outward, almost at the speed of light. There would be no warning, because no signal could outrun it. One moment, you would be sitting where you're sitting, and a moment later you would not be there anymore. Neither would the chair, the room, the planet, the sun, the galaxy. The wall of the bubble would not destroy them in a violent, fiery fashion. It would simply pass through, and what was inside the wall would be a different kind of universe, one in which you could not have been assembled. This is called false vacuum decay. Sidney Coleman wrote a paper on it in 1977, working out the mathematics. He calculated how often these bubbles might form, how fast they would expand. He showed they would grow at very nearly the speed of light. He showed that no warning would precede them. He titled his paper, The Fate of the False Vacuum. Whether our vacuum is the true vacuum or just a metastable one, we do not know. The mathematics of the Standard Model are consistent with either possibility. The lifetime of a metastable vacuum, if that's what we have, depends on details we cannot yet measure precisely. It might be enormously long, far longer than the current age of the universe, so you should not lose sleep over it. The chance of it happening in your lifetime is astonishingly small. But it could, in principle, happen at any time. Or it could already have happened, somewhere far away across the cosmos, and the bubble is on its way and we just don't know it yet. This is the price of empty space. The thing you thought was nothing has the power to end everything. Not because anyone is doing anything to it, just because that's the kind of stuff it is. So we come back to the jar, pick it up again, pour out the milk, pump out the air, block the photons, cool it close to absolute zero. What's inside? A roiling sea of virtual particles, a coat of Higgs molasses, an energy density that is either tiny or enormous, depending on how you ask the question. The answer's off by a factor that should embarrass us. A field configuration that may or may not be the deepest valley nature has to offer. A reservoir of activity larger than the activity of the matter we can see. You held that in your hand. You held the largest, busiest, strangest thing in the universe, and you called it empty. You are not the first to make that mistake. The vacuum has fooled smart people for a long time. It fooled me. The first time I started thinking carefully about quantum electrodynamics, about what the equations were really saying, I had to put my pen down and walk around the office. The implications take a while to settle. They're large. They're disturbing. They're also, I think, the most beautiful thing physics has discovered. Because here's what nothing turns out to mean. Nothing is not absence. Nothing is not silence. Nothing is, as far as we can tell, the underlying substance from which all somethings emerge. The particles you're made of are ripples in the fields of the vacuum. The forces that hold you together are exchanges of virtual particles in the vacuum. The mass that gives you weight is your interaction with the Higgs molasses of the vacuum. You are not standing on top of the vacuum. You are made out of the vacuum. You are a temporary, extraordinarily lucky pattern in the great, churning, mostly unseen ocean that pretends to be empty. There's a humility in that I find hard to put words to. The thing you most often dismiss is the thing you most fundamentally are. And one last thought before I let you go. There's a question you might have heard, one that's been asked since the ancient Greeks. Why is there something rather than nothing? It's an old question. It used to seem like a question that physics could not answer. But notice what we've done. We've discovered that nothing, the kind of nothing classical physics imagined, doesn't actually exist. The closest thing nature gives us to nothing is alive with activity, full of ghosts, layered with fields, simmering with energy. The universe does not have an off switch. There is no setting on the dial that says genuinely nothing. The minimum is not zero. It's a hum. So perhaps there is something rather than nothing. because nothing, in the strict sense the philosophers wanted, is forbidden. The universe could not be empty if it tried. The vacuum is structurally unable to disappear. Existence may not need a cause. It may be the only consistent option. Tell me this. Knowing what you know now, sitting wherever you're sitting, surrounded by the vacuum on all sides, doing what it does whether anyone watches or not, what's the first question you'd ask about it? What would you most want to know about the nothing that fills your room?